move to the next speaker, which is Ivana Beslic from the Institute for Radio Astronomy of the University of Bonn. She will talk about the dense gas properties and kinematics of NGC 253 with Alma.
Hello, everyone. Thank you for a nice introduction. I hope you can hear me well and also see my screen. So yes, I'm happy to be here and to see you all here actually, and also thank you for giving me the opportunity to present results of my recent and ongoing research. I'm a PhD student working with Frank Begill at University of Bonn, and I study physical conditions of molecular gas across local galaxies, how galaxies form stars from small to large scales, and most importantly, how this links to Milky Way studies and more vigorous systems at high redshift using observations from new generation telescopes such as ALMA and NOIMA. And this is exactly the topic of my today's talk. So now I'll try to motivate a little bit why do we need to study molecular gas and why it is important when it comes to understanding galaxy evolution. So I'll try briefly to introduce this rough sketch here. Galaxies are not isolated systems. Therefore, their evolution is regulated by gas exchanges with the surrounding medium, but also gas as galaxies, as they receive some gas, they also send that gas back due to feedback processes, due to star formation. So now let's take a closer look into galaxies. In particular, we know that stars form out of molecular gas phase. More precisely, star formation processes occur within the densest, coldest parts of giant molecular clouds that are shown here as blue circles. As it turns out, local overdensity or local overdensities of gas together with turbulence are fundamental drivers of star formation, and that is exactly what I'm interested in. In particular, I'm interested in understanding how dense molecular gas together with turbulence regulates star formation at scales of giant molecular clouds. Why is that even important? Well, it turns out that the star formation rate, molecular gas mass, atomic gas mass, and dust in galaxies have been varying over the cosmic time, as you can see here in these two figures. So the peak of star formation activity in galaxies occurred slightly before galaxies contained largest amount of molecular gas. And that result is interesting because it implies that the efficiency of gas into producing stars, or the shorter star formation efficiency, must be varying over the time as well, although we measure the constant star formation efficiencies in Milky Way. So it is our goal to link molecular gas physics to star formation efficiencies in a variety of environments, but also different times. It is very important to say that we gain significant knowledge about molecular gas content by studying well-known carbon monoxide. However, if we want to probe the densest molecular gas phase, we have to observe other molecules as well. So we need to observe molecules that start emitting a density significantly higher than the density at which CO emits. So we call these densities critical densities, and these molecules high critical density molecules. And these, altogether with CO observations, could be used to further constrain molecular gas density. And now I'll try to briefly explain you how. So let's look closer at this figure here that is from a recent theoretical study. So here are various line to CO1 to 0 intensity ratios ordered from low to high critical density. So on the low critical density part, we see various CO lines together with CO isotopologues. But on the other hand, at high critical density part, we see common high critical density molecular lines used within extragalactic literature. Each point here is color-coded by the volume density that is shown on the color bar, and also all points with the same color, i.e. the same volume density, are connected with solid black line. So let's now move from left to right, and we see that as we go towards high critical density molecules, we note the flaring pattern. What does this mean? It means that high critical density molecules relative to low critical density molecules such as CO can be used to constrain gas densities, because the flaring pattern actually reflects changes in volume gas density, densities, and it appears that high to low critical density line ratios are most sensitive to it. But now let's also look at what has been done within the literature so far, and this figure that shows a brief summary of some galactic and extragalactic work of dense molecular gas. So to first order, we see here that star formation rate on the y-axis scales linearly with the amount of dense molecular gas traced by HCN emission. This correlation goes from Milky Way clouds up to whole galaxies in their centers. And however, we note here, although this is a linear correlation, we see a clear scatter. So if we look closer, for example, here, I hope you can see my pointer, for the exact same amount of dense molecular gas, we note a variation of star formation rates by 2 orders of magnitude. And this is interesting, but also strange. And the explanation of this exactly lies in the physics of dense molecular gas at giant molecular clouds. However, to probe dense molecular gas at such small scales in nearby galaxies is extremely challenging task, because these lines are very faint in comparison with CO. So it is very time consuming to perform such observations, but this is exactly what we miss and what we aim to achieve using ALMA and NEMA, for example. So this is the goal of my study in particular, to fill this gap. And there are basically 2 possible directions which we could take. So the goal overall, what we want to achieve is to connect, to use nearby galaxies to connect our understandings with measurements in Milky Way, but also to connect our knowledge to more distant galaxies. And to do so, we have to not just map the classic spiral star-forming galaxies, but also more extreme systems in our neighborhood. So the primary goal of our research is to constrain molecular gas density and turbulence. The first direction we can take is to perform a high-resolution mapping of these high critical density lines, and also to connect with studies in Milky Way. But more also very important point here is that we can link dense molecular gas properties with other high-resolution datasets available. So to connect various gas phases using big surveys, such, for example, FANGS. In particular, on Friday, you'll hear a talk about FANGS ALMA survey by Jie Sun, but also there are other high-resolution datasets available, and also some datasets from GWST that are upcoming. On the other hand, the second goal is also to not just focus on the normal star-forming galaxies, so that's the main focus of FANGS survey, but also to expand our horizons and include other more extreme systems, such as Starburst galaxies. These are very bright in molecular gas, as shown here in this figure. So here is the spectrum taken towards the center of NGC 253, closest Starburst galaxy by ALMA ACA at 90 gigahertz range. So now let me briefly illustrate the high-resolution dataset. Results from this study have been published last year. And at the moment, this is the highest resolution dataset of HCN tracing gas across a large portion of a disk of a nearby star-forming galaxy, NGC 3627. This project has been a great synergy with other high-resolution datasets illustrated here. Now you may ask, okay, why do we even care about going towards small spatial scales? I already said these lines are really faint, and therefore their detection is time exhausting. But let me briefly try to prove my point here. So let's take a look at low-resolution HCN intensity map at kiloparsec scales, and also how this integrated intensity radially varies across this galaxy. And at kiloparsec scales, we note the bright center, we resolve galaxy disk. And also, if we look closer on this figure here, we see a smooth exponential decrease in line intensity, not just in HCN, but also in other line emission lines that are detected. However, if we jump to smaller spatial scales, so if we go further and deeper, we resolve dynamical features in these galaxies. So NGC 3627 is strongly barred galaxy, and we note some emission along the bar of this galaxy and also along spiral arms that we can see here, also that are very prominent in HST image. But this jump in resolution doesn't just impact the integrated intensity map, it also reflects the way we observe the radial distribution of the integrated intensity. So we also note here a certain environments that kind of pop up in emission. At the beginning of this talk, I introduced why do we need to observe other high critical density molecular lines and how we can use them to constrain molecular gas density. And for the first time, we were able to do so using observations. In particular in NGC 3627. So we repeat the exercise here. We order, so we explore various line intensity to CO2 to 1 ratios and order from low to high critical density. Also, we color code each point here by the CO2 to 1 integrated intensity, which is known to trace cloud scale surface density. And now let's also move from left to right, and we start seeing a flaring pattern that we expected from theoretical studies that is mostly prominent in HCN over CO2 to 1 line ratio. And this exactly confirms what we knew from theoretical studies. So HCN over CO2 to 1 is really sensitive to changes on cloud scale surface densities. But this is when it this whole story was now about the density. However, I also said that it's important to look at gas kinematics, as it can further enhance or suppress star formation. Depends on where do we look this gas. So
2 minutes.
Okay, thank you. So the point here is actually that we can use spectroscopic measurements to also constrain molecular gas dynamics. And in particular, we saw multiple velocity components in HCN emission across the bar ends in NGC 3627, as shown here. So these velocity components are associated with those previously identified in CO2 to 1 emission. And this is very interesting since bar ends are known to be intersections of bars and spiral arms. So we basically probe converging gas flows in this region. On the other hand, we also show strong environmental dependence on the observed spectra of HCN emission across the closed Starburst galaxy NGC 253, as seen here. In particular, sightlines originating from center and bar show multiple velocity features, and using the spectral decomposing analysis, we identified up to 3 velocity components towards these points. On the contrary, sightlines originating from ring and spiral arm are single-peaked and narrower. But this has further implications because eventually the dynamics of molecular gas affects the ability of the gas into forming stars. And in particular, when it comes to NGC 253 that you can see here, and also HCN emission obtained by ALMA ACA, we were interested now in checking how the ability of gas into forming stars act as a function of the amount of dense molecular gas that is sitting in certain environments. In particular, we were also interested in seeing how this environmentally depends. So we color-coded each sightline by the environment from it originates. And in particular, we see a strong anti-correlation between the star formation efficiency of dense molecular gas, but also with the relative amount of dense molecular gas that is sitting there.
1 minute.
Thank you. So basically, sightlines containing the largest relative amount of dense molecular gas appear to be least efficient at producing stars as opposed to other sightlines. Now I'll use this last minute to briefly summarize my talk. In the last 50 minutes, I tried to motivate why it is important to study dense molecular gas across nearby sources, as these are perfect to connect our understandings with Milky Way, but also with more distant galaxies. And these are, I showed two possible approaches to perform so. In both, we study gas density and turbulence. And it is, in upcoming years, it is essential to go further with cloud scale mapping of HCN emission, but also focusing on other more extreme systems in our neighborhood to complete the picture of dense molecular gas and its role in star formation. And with this, I would like to finish with my talk, and thank you for your attention, and I'm happy to hear questions.
Hi, Ivana. Thank you very much for this kind of study. Use multi-band observation, multi-scale. Very nice.
Thank you.
There is already a question in the chat.
Yes. You want me to read? I can read. So,
Yes.
Ivana, thank you very much. How did you calculate the HCN intensity in the center of NGC253? I guess there should be outflows and a part of HCN emission are absorbed.
This is a very nice question. Thank you. At this scale, so our observations are at around 300 parsec scales. Therefore, we are not able to resolve the outflow in that regard. So we proceed by calculating HCN intensity. We perform a standard procedure as usual. But it's very important to also say that HCN is artificially broadened in the center, and possible reasons could be that is HCN emission is further enhanced by the strong infrared emission, but also with the outflow. So, but that's something we should definitely take into account when interpreting our results.
Are you planning to observe all the sources, or it's enough to observe the central part like you did?
Other sources, do you mean like covering the whole galaxy disk, or?
Yes. Yes.
Yeah. So in this case, we observed the inner, if I recall correctly, inner 5 kiloparsec region. And this basically region is so within this region, we find the 90% of total CO intensity, so the 90% of total molecular gas mass, but also 85% of total star formation rate. This was achieved with ALMA ACA 50 hours of observations in total, as I recall. So it would be definitely interesting to observe the whole disk, but it is still challenging due to the time constraints.
Okay, thank you.
I have another question from the chat. So on 100 parsec scales, there is still a broad density distribution within the beam. So can line ratio tell us what the density distribution looks like?
That's interesting. That's something we have to also further investigate. However, it would be good to conduct such analysis to have more lines. And in this particular case, this was hard to achieve because, as you saw on this map, these detected molecular lines are actually really faint, and we didn't detect significant emission throughout the whole disk. So we needed to do some averaging to increase signal to noise ratio. Therefore, we were limited in that regard. But that would be a great follow-up using deeper observations of high critical density lines that are actually upcoming from ALMA, using ALMA.
I have one more question, if I still have time. Yeah. So thanks for the very nice talk. So it's very nice to see that this detailed analysis can be done in other galaxies, other than Milky Way, I think. So how would improve the analysis and interpretation if you could observe over transition of HCN? How critical do you think the limited number of observed transition is in the conclusion obtained so far?
So I didn't hear the first part of the question, so if it's not an issue, if you can repeat it, that would be.
Okay. If you observe more transition of HCN, you probably can improve the analysis and interpretation. So how much would you need? Or what are the how many transition would you need to improve your work?
The more, the better, definitely.
So how
that's for sure. For sure, HCN 3 to 2 and 4 to 3. That's definitely transitions that should be included and that we plan to include in our studies, because using different transitions are then we can actually do the theoretical do the modeling and then constrain physical conditions like gas density and temperature. We tried with this data set to do so, but our results were really robust in a sense that we need to include more analysis to be just to do to get a proper results.
And at some point, maybe the different transition are not tracing the same gas anymore, right? So then you come to
also, yeah, then we are actually entering different gas regime, probing different physical conditions, excitation conditions. Yes.
Exactly. So then you link to the problem of resolution, and you are mapping different scales and structures. So it's very
exactly. That is also, yeah, that is also that complicates even more.
Many thanks again, Ivana.
Thank you.